Hi, my name is Guillaume. I am an Android engineer on the career experience team. And today I'll talk to you about some of the unique challenges we are facing trying to develop a mobile application for Uber Freight. So we'll focus specifically on location tracking to see how it affects the UX of the application. So location tracking is a value proposition we sell to shippers. Shippers are moving very high value cargo through Uber Freight, sometimes more than $100,000. And obviously, they want to make sure that they know where their cargo is. And it also allows them to make sure that the system is reliable. And just the way you want to know when you order packages, if they will be delivered on time, shippers want to know. And also Uber wants to know if the system is on time. But before we get started, let's take a step back and let's see what it takes to move a load on the Uber Freight system. So from a user perspective, it all starts with an empty truck. Have the driver, after you have booked your load through the application, you will go to point A, the pickup facility, to get loaded. This is what we call deadhead. It's called deadhead because this part of the trip is done with an empty trailer and the driver is not getting paid for this part of the trip. This is common in the freight industry, and this is why we try to maximize and make better matching between drivers and loads to minimize this deadhead. Once the driver arrives at the pickup facility, he will get loaded, and then it's up to him to move this load from point A, pickup facility, to point B, the drop-off facility. Once driver arrives there, the truck will be unloaded, and ultimately, the driver will be available for his next trip, his next load that he can book and find through the Uber Freight application. This is from a user perspective. From a backend perspective, this trip is split between different states that all map to the current position of the driver. In order to map all those states and all those statuses to a position and a status, we use what we call geofences. A geofence is something very simple. All our trip flow depend on those geofences. It's made of a center, which is defined by a latitude and a longitude, and a radius. This defines a circle in which 3 different events will ultimately happen. The first event that we care about is the enter event. This is when the driver either arrives at the pickup facility or at the drop-off facility. We want to be able to record this event because it matters in order to automate the trip flow. The next event is dwell. This is when the driver is actually moving inside of this geofence without leaving it. Maybe the driver has to find a parking spot because all the cargo bays are actually busy and he can't just unload now. Then ultimately, later on, at some point in the future, we know for sure that the driver will have to exit this geofence. If we go back to our timeline, this is how it translates to location tracking for the Uber Freight trip flow. Before the driver actually starts the trip, we don't really care much about the location of the driver. It becomes really relevant when we arrive at the pickup facility because we want to make sure we record this state transition and we want to automate it to make it for a frictionless experience. Then at some point later, a few hours, the driver will exit this pickup facility and will start the main part of the trip, which is the distance between the pickup facility and the drop-off facility. During this state, when the driver is what we call en route, we don't care much about updates neither. We only need a few location updates to make sure that the driver is actually on time. But when things need to be accurate again is when the driver arrives at the drop-off facility. Here again, we need to be able to accurately record this enter event in order to record the time and move the trip to the next state. Then ultimately, the driver will exit this geofence, which will mark the load complete and delivered. As we have seen, accuracy is only relevant to boundaries of geofences. This is really important to make sure that we do not miss any important event. Otherwise, if we miss any of those events, the trip flow will end up being completely broken, and it means it will require a manual intervention from the user. Unpredictably, the product design we came up with for our application made it really hard for mobile engineers to come up with a reliable tracking system that works and operates at all time with very high confidence. And let's try to see and understand why this is happening. I'll show you two pictures, and we'll try to understand what are the main differences between those two pictures. On the left side, we can see an Uber driver user using the ride-sharing business application, and on the right side, we can see an Uber Freight driver. On the left, on the ride-sharing business, the phone is being plugged in, and the user is actually interacting with the application. We'll see why these two behaviors are actually tightly coupled together, why they matter, and why it makes it harder for us to develop reliable tracking systems that work at all time while drivers are moving loads between pickup and drop-off facilities. One of those main reasons is that trips between the ride-sharing business and the freight business operate at completely different time and space scales. Here on the top of the screen, we can see the scale for the ride-sharing application. In order to start a shift and to get started with the first pickup, a driver has to perform a few actions, a few manual inputs on the screen. He has to go online to accept a trip, and then he will have to follow in-app navigation instructions to go to the pickup location. Then once again, he will have to perform two manual actions on his phone. Confirm arrival, which is what ultimately triggers the SMS to the rider that let him know the driver is arrived, and then start the trip. This keeps the user engaged during this short period of time that is on average about 10 minutes. So there's no reason for the user to stop using the app and to turn the screen off. On the other hand, on the freight side of the business, things are completely different. Because we are not using a real-time dispatch model, but we are relying on a scheduled model, and the reason is that we need drivers to be able to book loads several days or weeks in advance, mostly because of this deadhead distance we discussed about earlier. Because you have to take into account this deadhead distance, because you know that it takes time for you to deliver loads, that you might have some delays, you want to plan your schedule days or weeks in advance. So we have this big gap between the search and booking experience and the actual start of a trip. This gap, that is about a day on average, is a gap between during which the user is very less likely to actually interact with the application. If we look at the next leg of the trip, which is from pickup to drop-off, we can see something similar. On the ride-sharing side of the business, in-app navigation is the biggest incentive for users to keep interacting with the application. Then once again, two manual actions that the user has to perform arrive at the end of the trip. Confirming drop-off and rating riders in order to be able to become open again for the next job and the next dispatch. Once again, we can see that the freight side of the business is completely different. Because we don't have truck safe routing navigation just yet, users don't have any incentives to use the application between pickup and drop-off. And because our trips are much longer, are operating across several states in the nation, this gap can last several hours, if not days, during which we might not have any interactions from the user in our application. We get a few, and this is what our system is trying to do. All right, so it used to not always be like that, actually. When we initially launched Uber Freight back in the end of 2016, the average trip flow was requiring between 8 and 10 manual inputs from the user in order to complete a trip. But because there was no other incentive to use the app, and because our users have been performing this job for decades without the need of an app, if we were not offering any other value in this app, users were just keeping the phone in their pocket. They were not performing the manual checks, and we ended up with a completely broken trip flow that had to be resolved manually over the phone through some support calls, which made for a very frustrating and irritating user experience. So we started to automate most of the steps and to make it easier and simpler to use. So because we have initially no incentive to use the app, we started to automate the flow, to simplify it. And it means we started to rely more on the GPS and on the geofencing systems. So we created this sort of vicious circle where every time we are trying to make the app simpler, we are also making our users less prone to use our applications because there is less reasons to open the application because everything is becoming more and more automated, which ultimately led to some contradiction. Because there's no incentive to use the application, our users are not interacting with the application, which means that ultimately they will unplug their phone, which means that on modern OSs, some power-saving modes will start to kick in, which makes it harder for the application to collect location in the background and upload this location to the Uber servers. So it means every time we are making the application simpler, every time we are trying to rely more on the GPS, we are also making it harder at the same time to rely on the same GPS system. The reason is that power usage is key on our devices. If we are not already offering good value proposition to our users through our application, we have to ensure that the application is light and is not draining the battery of our users. Otherwise, of course, they will uninstall it and stop using it. On modern OSs, the trend is to prevent applications to perform long-running background operations without the user even noticing it happening. On iOS, if you go to your battery settings, you can see which applications are using the most energy on your phone, making it likely for users to uninstall power-hungry applications they are not using. Same thing happens on Android, and actually some manufacturers are going even further. And here we can see on the GIF an example of Samsung on the Galaxy S8, where they are actually sending a notification that invites users to put applications to sleep when they are using too much power in the background without the user actually interacting with the application. As the name suggests, when an app goes to sleep, it becomes really hard for developers to make it able to reliably send location over the network. Now let's see how all these translate in the Android world specifically. During the next few slides, I'll be talking about backgrounding applications and foregrounding applications. The event of backgrounding application is what we do when, for instance, we stop using an application or the user switches to another application. It means the application is not rendering on the main screen and is not being shown by the user. On the opposite, foregrounding an application means going back to this application and starting interacting again with this application. So when an application is being sent to the background on the Android system, it will be put in some sort of LRU list where it will be up to termination by the system. The main reason is that mobile environments, and Android as well, are memory-constrained environments where the system has to be very aggressive to kill applications that are not being used in order to make room for other applications the user actually cares about and is actually interacting with at the moment. If we take a quick example, let's say that you're consulting Facebook to look about meetups and events around you tonight, and you find this meetup. Then maybe you will open some sort of chat application, and you will ask your friends if they want to come with you to this event. Then the next step will be maybe to open Google Maps and get directions to this building to attend the event. When you do so, when you open Google Maps at the end, both Facebook and the chat application has been put in the background and are up to be killed and paused by the system because maybe it needs more memory to let Google Maps perform some sort of fancy rendering and do turn-by-turn navigation for you. This is even more true on low-end devices where there is even less memory available for applications. This mechanism that we call system pressure, and that is very old actually, is affecting all the devices or applications are running on, starting with Android 4.1, which is the oldest version of Android that we are currently supporting. Then came Android 5, where Google introduced something new called battery saving mode. Initially, battery saving mode is an automatic mechanism that kicks in when the device has less than 15% of battery remaining. When this happens, it will automatically turn off animations. It will stop some of the long running background operations, and it will show some sort of like orange banner to make the user aware that he should plug his phone as soon as possible. So this is one of the first mechanisms that makes it harder for us to keep tracking location while drivers are on trip for a long time. Some manufacturers even go further, especially Samsung, who tries to ask the users to have this power saving mode turned on at all time to artificially increase the overall battery life of the device. Next came Android 6. And in Android 6, Google introduced two new power saving mechanisms. First one is called doze, and kicks in when the device is standing still and the user is not interacting with it. So original use case that has been presented with it is the nightstand. When you come back home and if you just drop your phone and put it on your nightstand, after a while, it will stop some of the applications that are running on it, and it will prevent network access for these applications, and it will prevent location provider access to these applications. Second method is app standby. App standby will kick in even for moving devices, but this one only affects applications that the user hasn't interacted with in a long time. Then comes Android 7 with Doze Lite. Doze Lite is an extension of Doze, and where Doze was only starting when the device was standing still, this one can start even when the device is still in motion. It means if our drivers are turning the screen off and putting the phone in their pocket, even while they are operating a vehicle, Doze Lite will start to prevent applications from collecting location and sending it to Uber servers. Then finally, with the latest iteration of Android, Google introduced two new limits that are called background execution limits and background location limits that actually target exactly what we are trying to do with the Uber Freight application. On top of that sits our application that has to comply with all those layers of power saving in order to be able to correctly collect this location information and also be able to send it back on time to the Uber servers. Fortunately, we have a few tools in our toolbox to work around those power saving modes. We have job scheduling, which is an attempt at batching background operations together to save on battery and making it more efficient for developers to perform background location. We also have client-side geofences. Client-side geofences allows us to wake up the app when the device figures out that it breaks in or out of a predefined geofence. We also have alarms, which is a way for applications to wake themselves up after a specified amount of time. And we can also rely on Firebase cloud messages, high priority messages. Basically, transparent, invisible push notifications that we can use when we need them in order to wake up the app, even if it's in deep sleep mode. Long story short, permanent long polling in the background is not an option anymore. Otherwise, it will probably break because at least one of those power saving modes we just saw before. So it means we have to be reactive to and smart about how we collect location and how we detect location changes. While we were developing this location collection pipeline on Android, we were relying a lot on this battery historian tool that I highly recommend you if you're an Android engineer. It's an open source tool developed by Google that allows you to quickly and efficiently monitor battery usage on your phone. It's very easy to use. You just pull a bug report from your device, plug it into this tool, and it will draw this kind of timeline that shows you exactly what happened on your device over the past few hours. You can see on an app per app basis what was running, what was consuming GPS, Wi-Fi, what was putting up some wake logs, everything that actually adds more power consumption. And on the same timeline, you can see when those power saving modes are starting and stopping so that you can see how they are influencing each other. If you are ever developing an Android application that has to run in the background for a long time on all the versions of Android and on all the devices, you want to make sure that you actually thoroughly test your application through every and each of those power saving modes, because otherwise you can end up with a very unexpected behavior that ultimately for us might break the whole trade flow. Ultimately, this has been the opportunity for us to work on some very unique challenges. Most of the other Uber applications don't have to worry about these kind of limitations, mostly because users are only using those applications for a short amount of time, like 10 or 15 minutes, or they don't have to perform long background operations. This allowed us to increase our deep understanding of all of those mechanisms on the different OSs on both iOS and Android.